Hey everyone, hope you're doing fine and staying safe and healthy. First of all, I would like to thank the organizers of the Embedded Vision Summit for making this virtual platform enable to for us to present our ideas and for us to interact. My name is Vaidyanathan Krishnamoorthy. I'm an architect with the Edge AI team, part of the IoTG business unit at Intel Corporation. I would like to present the Federated Edge Computing System Architectures, which is an interesting topic and of interest to a lot of our customers as well. As part of the agenda for today's presentation, I would like to briefly present you with the need for edge inferencing and run you through with the different use cases and scenarios where edge inferencing is deployed. And I also will briefly touch on the Intel products that addresses this edge inferencing needs. So if you look at an edge where a discrete set of different compute nature devices being connected, and you one cannot get all the data to the cloud to do further inferencing or processing of the data to make decisions. If you were to look at an autonomous vehicle, uh, the low latency or real-time decision making is of essence. So the compute needs to be happening, the inference needs to be happening at the edge where data is generated. In addition to this technical challenge, there's a lot of security and privacy regulations, which is also mandating the data to be processed where it is generated, which is the edge. Because there are a lot of regulations today that do not want the data to be sent to a remote data farm and then taking care of the processing. So, with all this uh, technical challenges and the legal challenges, it's best to do data inferencing at the edge where the data is generated. With that, let me take you through some of the deployments that we have seen, and I'll explain you how we resolved some of these challenges and what are the advantages of these architectures. First off is a very small retail or a residential kind of a deployment where we have very handful of cameras that could be connected to the cloud through a camera controller, which can connect it at a similar to our homes, or it could be video as a business model where IP cameras get connected to the cloud directly. Some of the use cases are very simple here. For example, person detection to detect somebody walking in front of your door, and then detecting and recording it and sending it out. Or it could be in a small retail like people counting, which is a very popular application in the COVID era where we have restrictions on the number of people given the square footage of a retail store. So these are simple use cases which can be done with a handful of cameras. Some of the challenges with this kind of a very simple deployment is it cannot be used for any latency critical usages. Also, the bandwidth needed when the number of cameras that increase is also poses a challenge on sending all the data to the cloud. Uh, this is a very typical deployment that you see in a large retail store where at least there are some few tens of cameras getting connected and few sensors that can be also attached to it for making decisions like smoke sensors or carbon monoxide sensors and other stuff, where traditionally the video was processed as NVR boxes, network video recorders, and some storage boxes, where for digital safety and security, people used to record all these videos and keep it. But now there is a lot of value that can be derived from this data, and the retail use cases are growing by the day, where people want to do people counting, for example, or how to do shelf monitoring instead of running around to find if the shelf is empty, stock is available. So those can be automated by deploying some cameras and making some inferencing happening. And you can also do kind of demographics to understand how you want to improve your business by addressing the population that is walking into the stores. So such deployments can be done by adding additional compute at the edge, which is at the retail store location, and the data need not be sent all the way to the cloud to make all this decision happen. And the way to do this is we can create a small cluster of computes orchestrated by open source orchestrator frameworks like Kubernetes. And by deploying container workloads, we can realize the use cases and also scale up and down the amount of compute needed based on these compute needs, inferencing needs, and the use case needs. The advantage of doing some of these deployments using cloud native frameworks is also high availability and reliability. For example, if one of the node goes down, it can be always the workload can be moved to the other uh, compute available in the cluster, and it can be managed. And another important thing is it does not need always on connectivity to the cloud. It can operate with intermittent connection to the cloud, and decisions are made locally at the edge for all kinds of alerts to the store manager, or all those activities can be done at the store. Another popular advantage of this using the cloud native frameworks is you can alter the workload based on the you can alter the compute based on the workload needs. And when the store is open, there will be a lot of inferencing workloads. Whereas when the store is closed, the retail store is closed, it can be used for retraining some of the models or improving the accuracy of the models with the same set of compute available. So it can be, it is a scalable solution. And the best principles of the cloud architecture is coming into the edge side, where we can deploy it on a scalable hardware, whether it can be deployed using, say, a small 3 NUCs, or all the way to managing few Xeon servers. Let me explain you this with this architecture of one of a very popular open source orchestrator, Kubernetes, which can actually manage diverse set of heterogeneous hardware, and it can deploy workload based on the compute needs of the workload. And the way it can be done is it can be realized as small as 3 NUCs, Intel NUCs, or all the way to a half a rack of server or racks of server, which anyway is deployed in cloud data centers. So the advantage is it can be used to orchestrate edge servers and do analytics workload. And it can also be used for long-term storage. The long-term storage beyond some point can be pushed to the cloud. It can work well with the cloud on the back end, but also make autonomous decisions at the edge to take care of edge deployments completely autonomously. And the way it can be done is, for example, from the advantage of having a cloud backend to this is primarily a retail store chain can manage thousands of their stores across the nation by deploying these such Kubernetes edge clusters, and can be managed them through the cloud. The cloud again is used for pushing in updates from the software updates and manageable stuff, or you can alter the workloads based on the needs. So for such situations, the cloud is used, but otherwise the edge can make its decision on its own, and take care of all the workloads that is needed at the edge. This is another representation of the same architecture, where I have drawn the software frameworks for a Kubernetes worker node as well as a Kubernetes controller, where the controller communicates to the cloud backend on one end. The other end, it takes care of all the compute nodes available for scheduling workloads. But at the same time, one of the worker node can also act as a backup controller if the controller node goes down. So we don't have the problem of the one node going down, bringing down the entire cluster, or the retail store not having connectivity or not being able to do any workload. So this is a very important advantage of realizing an edge cluster using cloud native frameworks using elastic compute and storage needs primarily. This is an edge cluster popularly mostly used for smart city or a larger block kind of residential block kind of applications where the deployment is not bound by a single building or one or two buildings, and it has to span across a geographical area, and it can be realized where example the AI appliances that I have marked here could get connected to a few cameras and can be mounted on a light pole. And the AI appliance can be a custom built hardware just for doing inferencing of the data that is coming through that camera feed and pass on the metadata to the backend Kubernetes controller for storage or for the cloud backend if further storage is needed. So such devices can be diverse set of heterogeneous hardware can be managed using Kubernetes cluster, and the workloads can be deployed based on the location, based on the needs, and based on what is the compute available. And it is also possible that the same camera workload can be connected if additional workload is compute are need. An additional AI appliance sitting in the same network can be utilized to run some of their workloads. For example, if there is a sport event in a one block of a city center where the compute needs are much higher for a particular time, that can be scaled up without going and adding permanently another box or a compute to it which cannot be used other times, because the same workload camera feeds can be brought into multiple AI appliances connected across this cluster to do the additional workload, whereas the other side of the city where the block some of the blocks are completely empty and you don't need so much compute to do some of those workloads. So scaling up and down of these workloads, high availability and reliability are some of the key factors when we deploy again heterogeneous hardware, custom built hardware for edge inference like the edge Intel Movidius hardware, or even general purpose compute like the Intel Xeon and the core servers, to realize these edge systems which can be deployed for varying compute needs. Another popular use case is a smart factory use case. With 5G network becoming very popular, and we will start seeing 5G private networks being deployed at larger enterprises and larger complexes like smart factories, where multiple of these sensors can be connected using the 5G private network. One of the key challenges of a smart factory is that the data is not to be sent to the public cloud. No factory wants to send the data to a public cloud. They want to keep it within their premises. They want to make all decisions based on their data within their premises. So the edge cloud is a very key factor. And with 5G, most of the networking related concepts are also software turned. So it becomes very easy and nice to actually deploy all this as software, and the edge cloud takes care of the multiple inferencing needs. Again, within a smart factory we need varying inferencing needs at different levels. For example, there is a camera fitted to a machine which will monitor the quality of the product which is coming out of that machine, has its own inferencing needs to take care of the quality of the product. And again, if you look at inferencing needs at a factory floor where multiple of these machines are being monitored, then the computing needs and the inferencing needs are different. Inferencing algorithms are different again. And at a factory level, the inferencing needs are again very diverse and very different, which has to take care of thousands of these such sensors and monitors, all the data coming out of the factory, which will enable the factory to make a lot of decisions based on data, and that helps the factory environment to be run very smart and very efficient. And the advantage of using cloud native frameworks is all about managing the infrastructure and the workloads very efficiently. This is an evolution of the edge cloud in my perspective. If you look at the left, you see that originally the clients wanted to communicate to the edge, and the edge needs were very evident for making real time decisions. But the addition of a public cloud uh, enabled to manage such multiple edge clusters across geographies. So that's the next step of evolution that we are seeing today, where the public clouds are managing multiple edge clusters across geographically dispersed. And now with 5G connectivity, the telcos have started realizing the value of their pipe much more than what it used to be. They provide the communication pipe connectivity for all the edge to the public cloud. Now, telcos will start providing metro cloud at the edge for at the city level, for example, where they have their metro data centers, and they can provide a lot of edge connectivity and complement a lot of uh, what the public cloud providers provide to the edge. So it will be a good combination of edge clouds combined with telco edge and the public cloud, which is actually starting to emerge as the future edge that we foresee. Let me give you a very brief on the different Intel products that address this edge inferencing market. Uh, we definitely need a scalable general compute like the Atom class, the Core class, and the Xeon class of compute, which also has now extensions to do edge inferencing like the bfloat and the dl boost kind of inferencing extensions available to these architectures. In addition to that general compute, we also have purpose built hardwares which are like the discrete graphics or the FPGAs and purpose built edge inferencing hardware like the Intel Movidius hardware, which can be added as uh, accelerators to this general purpose compute, so that it creates a good chain of products available for different scale of compute to do edge inferencing, which enables us to deploy very efficient edge cloud deployments or the edge inferencing cloud deployments. In addition to the hardware, we also have software frameworks like OpenVINO, which is like writing the inferencing application once, and it can be deployed on any of this hardware, Intel hardware, so that the developer need not take care of the intricacies of the hardware, and the software can be deployed on the most efficient hardware based on the performance needs that is needed for the application. So overall, Intel provides a set of hardware products, software enabling the entire edge infrastructure, which can be addressed for the market. So, just to recap, the edge inferencing needs are very critical with respect to real time decision making, and added to that, the security and the privacy reasons for edge deployments is increasing. uh, the cloud native frameworks, which were very popular in the public cloud infrastructure, have started being very effective at the edge as well. It needs some tuning to be made work on the edge, but overall, I think Intel has been a very active contributor to these cloud native frameworks. So we understand these frameworks very well, and these are already optimized to run on Intel hardware. So the deployments at the edge as well as the cloud work very seamlessly across Intel products. So with that, I would like to open up the floor for questions.